In this video, we're going to be talking about a topic in organic chemistry, specifically pertaining to stereochemistry, known as conformational analysis. So to describe conformational analysis, we first have to describe what a conformation is, or a conformer. So conformations are different 3D arrangements caused by rotation about a single bond. So basically all a conformation is, or a series of conformations, is rotation about a single bond such that we get different 3D arrangements in space. So let's talk about a particular molecule, one that you may know. This is H2O2, or hydrogen peroxide. If we were to draw the Lewis structure of hydrogen peroxide, we would see that we have an H, we have an O with two lone pairs, and then we have another O with two lone pairs, and then we have an H. So we get kind of this, we could call this an anti-structure with the H's. However, we can imagine if we rotated this single bond around such that this hydrogen came up here, we could end up with a structure that looks less like that anti-conformation, and instead something that looks like this. We could call this a cis conformation or something like that. And this is a 180-degree rotation. We would call these two molecules, this one on the left and this one on the right, we would call these conformers, because the only difference between these two molecules is that we've rotated one single bond 180 degrees. Now, rotations do not have to be 180 degrees. They can be less than or greater than 180 degrees to form different conformers. But in this case, we can see that we actually have a range of conformers of H2O2. We could have anywhere from these two would be planar arrangements of H2O2. We could also have non-planar arrangements of H2O2 where we have something between these two variants, and we would have a whole host of conformations of H2O2, but you can see that the two extremes of these would be rotating 180 degrees. So it is often useful, like we've seen in organic chemistry, it's often useful to have different ways we can display certain characteristics of a molecule. And when we're talking about conformations, it's often useful to talk about what we call, that's an M, Newman diagrams. So Newman diagrams are going to display conformations about a single bond. So I think the best way to describe what a Newman diagram is to show you how to construct one. So let's look for a second at C2H6, or this would be known, as you can see now from your naming unit, this would be ethane. We can also write this as H3C CH3. If we're drawing this as a diagram showing all the bonds, we would have we have two H's, so we'd have two going up, we'd have two coming out, we have two coming out, one on each side, and two going into the plane. Remember that a wedge bond that's displayed here is coming out towards you, and a dash bond or a hash bond is going away from you into the plane of the board. So when we're constructing a Newman diagram, we choose one of the bonds in the molecule, and we are going to rotate the molecule such that that bond is going directly in and out of the page. So what do I mean by that? So in ethane, there's really only one major bond to choose, and that would be this CC bond. And what I'm going to do is I'm going to imagine that I'm looking straight down that CC bond such that the C on the left is in front, and directly behind it is the C in the back. So the way we draw that is we're going to draw a circle, and then we're going to put a point in the center. That point represents this bond here. So the C directly on top of another C. And then what we would see if we look in this direction is we'd have an H pointing directly up, an H pointing towards us, and an H pointing away from us. Now I'm rotating this this way, so that means that the H that is coming out of the board will be on the right. I also have the H pointing directly up, and I have the H that is going away from me that is going to be pointing to the left. So those are going to be my three H's, and I will write those front H's in red so we can distinguish between these. The front H's are going to be in red. Now the back H's, the ones on this carbon, are also going to be similarly placed. You know, we have this H and this H that are going to be directly on top of one another. And the way we draw that on, I can't draw it directly behind it, so I'll draw it off to one side to show that it's directly behind it. This one that's pointing out is going to be directly behind the one that's pointing out in the front, so I'll draw that a little bit off to the side. And then the one that's pointing back is going to be behind the one that was pointing back in the front. And again, I'll draw that a little bit off to the side. So this would be what we call our Newman diagram. Our C's are directly behind one another. There's a C here in the front, and there's a C there in the back. We have our three H's in the front and our three H's in the back. Now there's two different arrangements that are important when we're talking about Newman Newman diagrams rather. If we have this arrangement where we have the H's directly behind one another, we call this eclipsed. So an eclipsed arrangement is going to have the bonds directly on top of one another, front and back. But you can imagine if we rotate this molecule, if we take this these back hydrogens and rotate it 60 degrees to here, so we're rotating it 60 degrees to here, and we rotate this 60 degrees to here. So I'm rotating it 60 degrees clockwise. So I'll draw this here. This is a 60-degree clockwise. We end up with a slightly different Newman diagram. So we have the three in the front that are pointing the same way as we had before. One off to the right, one off to the left, and one directly up. And now the difference is we're going to have those back bonds not on top of one another, but directly bisecting these two bonds. They are at 60-degree angles to one another. So the H's are in between the front H's, as we would say. So if the top one, this one where they're on top of one another, is called eclipsed, we call this bottom one staggered. And staggered, as we will see, is much more preferable than an eclipsed structure. Intuitively, we can think that if we have two hydrogens on top of one another, those electrons are going to clash. That is called steric clash or steric bulk. And when we have them spread apart, it relieves that steric bulk or that steric clash such that we can have a lower energy conformation. So these two would be conformations of one another because all we've done is rotate the single bond. So we eclipsed and staggered forms of Newman diagrams are indeed conformers of one another, and where staggered is always going to be more preferred than an eclipsed structure. So let's, for a second, examine the rotation about the single bond in ethanes, and let's do actually a conformational analysis. So conformational analysis examines the rotation about a single bond and energy levels upon rotation about a single bond. So let's draw a large graph here. So this we can call this is the angle of rotation. So we can call this this is called the torsion angle, which is the angle of rotation. That's going to be in degrees. And this is going to be our energy level. So we're going to start with a torsion angle of 0. So we could call this 0. And what we're going to have is and I'm only going to draw two hydrogens just for ease. And we're going to have them right on top of one another. Remember, this is high energy. So we have two hydrogens that are right on top of one another. And this is going to be our eclipsed variant of the conformer. Now, if I rotate 60 degrees, We're then going to have a conformer that is staggered. So those are going to be bisecting those angles. And remember, these are filled in with hydrogens. This is going to be staggered. This is going to be a trough because remember, staggered is lower in energy than an eclipsed conformer. So this is going to curve down. If I rotate it again 60 degrees to 120 degrees, we're back at an eclipsed form where they're right on top of one another. And sorry, that's off the board. And remember, these are all hydrogen, so there's no real preference between these two eclipse forms. So they're going to be the same energy level. So this energy is going to curve back up as we get another rotation in. We're then going to rotate another 60 degrees to 180. We're now at the another staggered conformation. And again, because these are all hydrogens, there's no preference for the staggered conformations. So this is going to be the same energy level as the previous staggered conformation. And that's going to curve down. You can kind of see how this is going, but I'll just do it all the way out. At 240 degrees, we're at another eclipsed variant where they're all on top of one another. We have an H up here and now an H back here. Again, same energy level, so it's going to come back up. We rotate another 60 degrees to 300 degrees. We're going to be back at a staggered conformation where we have an H here. Our last H is there. We are at the same level because those are all H's, so there's no preference. That comes back down. And we're then back at the beginning, 360 or 0 degrees is going to be the same. We are back at the original eclipsed position where the H's are right next to one another. And we are back at the high energy level. So what we see is in the conformational analysis of ethane, we really only have two energy levels. We have our high energy level and we have our low energy level. So what that means is that any one of these three staggered conformations is going to be preferred. They are degenerate. They are the same energy level. So neither of them is preferred over one or the other, but they are preferred over the eclipse variant. So we will see staggered variations in ethane. So this is when they're all the same. But what happens if they are, what if these energies are not the same? And for that, we need to examine a more complex molecule, which we will do next. So let's move on from ethane and then look at butane. So butane is going to be CH3, CH2, CH2, CH3. And what I'm going to do is look at this CC bond for my conformational analysis. So what that looks like is I'm going to have a CC. I'm going to have two H's, because those are both CH2s. And then I'm going to have a CH3 coming up in the plane of the board. So let's draw the Newman diagrams looking down this bond. So I'm going to be looking down this CC bond, and I'm going to draw it the same way as we did before. So let's start. I'm going to label the front in red, and I'll do the back in blue. So let's start with our front carbon. So we have our point in the center, that's our carbon. We have our CH3 pointing directly up. And keep in mind, now I've rotated it out of the plane in such that this H that is in the front is going to be on the right. So I have this H over here. I have my CH3 pointing up, and I have my back H pointing to the left. Now you'll notice that this CH3 is also pointing up, this H is pointing out, and this H is pointing in. So you can guess that this is going to be our eclipsed variant. So I'm going to just put this off to the side. I'm going to put this off to the side. I'm going to put this off to the side. So this is our eclipsed variant. And in fact, this is the, of all of the eclipsed variants that you can imagine, eclipsed conformers for this molecule, this is going to be the highest in energy because we have two CH3s that are directly on top of one another. We call this torsional strain. So this is torsional strain. And that is caused by two large groups being eclipsed with one another. So this is at 0 degrees. They are eclipsed, and the big groups are eclipsed. Remember, hydrogens are small. Methyl groups are not so small. So this eclipsing fashion is very unfavorable. So let's rotate this back one 60 degrees, so we'll do a 60-degree rotation. We are once again left with the front carbons, the front substituents being the same. We have two H's and a CH3. And then we're going to look at the back carbons, and we've now taken this methyl group and we've moved it right here. We have a methyl group bisecting those two bonds. We have an H in the back and we have an H in the back. What we see is this is, again, they are bisecting, so this is staggered. What we also notice is that there's a special name for when we have the big groups in this arrangement to one another, where they are staggered and next to one another. So if they are staggered and 60 degrees apart, like they are, again, it could be 60 degrees on either side, but they are staggered and 60 degrees apart, we call this arrangement gauche. So gauche is going to be this arrangement. They are still near one another. It is not the perfect arrangement, but it is a little bit better than having them eclipsed. So let's go from here and rotate another 60 degrees. So I'm going to take this CH3 and I'm going to rotate it to this position. You can already kind of guess that 60 degrees from here is going to be another eclipsing conformation, so we can anticipate that it's going to be higher in energy. And in fact, we see that it is higher in energy. We have the CH3 eclipsing this hydrogen, we have a hydrogen eclipsing this one, and we have a hydrogen eclipsing this one. Now, if we were to compare this eclipsing conformation and this eclipsing conformation, we would see that this eclipsing conformation, which would be at 108, this would be at 120 degrees torsional angle. This was at 60. This 120 degree torsional angle is a little bit lower in energy than the 0 degree because we have eclipsing, yes, so it is a peak, but we don't have the big groups eclipsing each other. It's a big and a small group, a hydrogen and a CH3. Since we have this division in energy, or this division in steric bulk, it is a little bit lower in energy than eclipsed. However, it is going to be higher in energy than gauche, because gauche is staggered, and staggered is always lower in energy. If we rotate this a final 60 degrees, I'm going to take the CH3 and put it over here, so it is staggered again. We can imagine that since it's staggered, it's going to be lower in energy than the eclipsing conformations. And what we'll notice is that this one is even lower in energy than the gauche conformation. We have hydrogens here, and we have a CH3 here. You'll notice that these CH3s are 180 degrees apart to one another. If this is staggered because they are bisecting the bonds. However, if we see two large groups that are trans to one another, or 180 degrees apart to one another, we have a special name for this, just like we have a special name for this one over here. We call a 60-degree torsional angle or dihedral angle gauche. We call a 180-degree dihedral angle anti. So this angle is 180 degrees. This is the dihedral angle, and this one was only 60 degrees. 60 degrees is gauche, and 180 degrees is anti. If we were to rank these in terms of lowest to highest energy, we would see that the anti is going to be the lowest energy, followed by gauche, because these are both staggered, followed by the eclipsed, where the big groups are not one on top of one another, and then highest in energy would be the eclipsed, where they are on top of one another. So again, eclipsed is always going to be higher in energy than staggered, and gauche, within staggered, gauche is going to be higher in energy than anti. And that is across the board universally true. So let's draw a conformational analysis of butane, the same graph that we did for ethane. And what we'll notice is that since there's differences in the eclipsed and staggered, that the conformational analysis is going to have peaks and troughs that are different. So again, we'll draw a graph. This is going to be our angle, and that's in degrees, and this will be our energy. All right, so let's begin. And in this case, I'm only going to draw the CH3s. So we start with the eclipsed, a torsional angle of 0. So we've got the two methyl groups eclipsed to one another, and as you can imagine, this is going to be our highest energy. So this is at 0 degrees. So that's 0. If we then rotate to 60 degrees, I'm going to make it a staggered conformation. We are going to drop down in energy. It's staggered and it's gauche. So we're going to have something that looks like this. We have our CH3 here and our CH3 here. So we're going to drop down in energy to something like here. So we would have a peak going to a trough. We're then going to rotate to another, at 120 degrees, we're going to be eclipsed again, but this time it's going to be a little bit lower in energy than this first eclipsing interaction because we are not eclipsing the large groups, we're eclipsing a large group with a small group, so this CH3 is over here. So this is going to be slightly lower in energy than the original eclipsing interaction. It's going to still be a peak though because it is eclipsed. Excuse me. And then if we rotate to 180 degrees, we are now at our most favorable anti-conformation, and that's when the CH3s have a dihedral angle of 180 degrees to one another. So this is going to be our most favorable interaction. This is very low in energy. And this is going to be, what we'll see is for all alkanes, even higher alkanes, this trans fashion will dictate the structure of the individual alkanes. If just to complete this conformational analysis, we then go to 240, we are at an eclipsing interaction again, where we have the CH3 eclipsing a small group. So it's going to be higher in energy than staggered, but lower in energy than the original eclipsing interaction. So we have a peak, but it's not as low, it's not as high rather as the highest peak. We're then going to come down to a staggered conformation, and this is gauche again. So we have another gauche conformation, except on the other side. Gauche doesn't determine which side it's on. It just means that the dihedral angle is 60 degrees. So we have another gauche interaction. So it comes down in energy. And finally, and that is at 300 degrees. And finally, at 360 degrees, we are back at the peak of our unfavorability. We are at the methyls being eclipsed with one another, and that is very unfavorable because it's the big groups. The torsional strain is huge, so we were back at a peak again. Just to relabel this, if we're looking, this is going to be eclipsed. We have eclipsed, eclipsed, and eclipsed. Then in between, we have our staggered conformations. And then remember the staggered conformations, some of them have special names to them. When we are at 60 degrees dihedral angle, we call it gauche. And our lowest energy conformer is going to be our anti, where we have the CH3 groups 180 degrees apart from one another. You'll notice that this 180 degrees dictates why we draw our alkanes in zigzag patterns. So if we draw something like this, if we draw butane like this, you'll see that this group, this CH3 group, and this CH3 group are 180 degrees dihedral angle apart to one another. So higher alkanes are always drawn as zigzags because we want to minimize the conformational interaction by having them in anti. So everything in this case is anti to one another, which makes it the most stable conformer that you can possibly have.